Welcome to MEI Mechanics. We're on the topic of forces and moments, and this is video 1.4, ladders. Now, if we're dealing with a problem involving a ladder, we're going to model it as a rigid body in contact with two surfaces, the horizontal floor and a vertical wall, and there'll be contact forces at both of the ends of the ladder where it's in contact with the floor and the wall, and we'll model those in the usual way, splitting them into a normal reaction force and a frictional resistance force. So here's our first example. We have a uniform ladder. That's important because that will mean that the centre of mass of the ladder will be halfway along, and it's got length 8 meters. One end against a smooth vertical wall. Well, that's important because that means there'll be zero friction at this point. But the other end is in contact with a rough horizontal ground, so there will be friction here. And it also says the ladder is on the point of slipping, and that's also crucial for this question because it means that that friction will be limiting friction, and it will be at its maximum value, F max, which will be mu r. Now it says the base is 4 meters from the wall, and it wants us to calculate the coefficient of friction between the ladder and the ground. So the first thing to do here, really, I would suggest, is to think about the geometry of this situation. So we're told that the ladder is 8 meters long. The centre of mass, because it's uniform, will be halfway along, so that centre of mass will be 4 meters from either end. And also, we're told that it's 4 meters from the ground. Now, if we think about what that means geometrically, imagine if I was to reflect this in this vertical line, I would have an equilateral triangle, and therefore this angle is 60 degrees. And this angle here is 30 degrees. And this height will be 8 sine 60. Which is the same as 8 times root 3 over 2. So we can say that's 4 root 3, that height. Right, so what we need to think about now are where there are forces acting. So from that centre of mass, there'll be a force acting on the ladder. We don't know what the mass of the ladder is. We can usually assume that means that this isn't going to depend on the mass. So we'll just call that mg for now. Then on the wall, well, there's no friction. We're told it's a smooth wall. So the only force acting from the wall will be this normal reaction force, and it has to act normal to the surface. So the normal reaction force here will be acting in that direction, and the normal reaction force here will be acting vertically upwards. Now if I call that R, it's going to make sense to call that one R because that's the one that's we're going to be combining with the idea of friction later. I can't call this one R because I don't know if they're the same size, so I'll give this a different letter. Let's call that S. Now at this end there's going to be another force acting, the friction, and that's acting to stop the ladder from slipping. Now the ladder, if it was to slip, would want to move to the left, so that means that the friction must be acting to the right, like that. So there's the friction F. Okay. Now we need to try and resolve some forces. Let's start with the vertical direction. So if I resolve in the vertical direction, then what forces are acting? Well, I have the normal reaction force R acting upwards, and the weight mg acting downwards. So I have R minus mg equals 0 because it's in equilibrium, and that tells us that R itself is equal to mg. Now let's resolve horizontally. Acting to the right, we have the friction, F, and acting to the left we have the reaction from the wall, S, and because that's acting to the left we'll put a negative sign in front of that. That has to equal 0 as well. So that means that F is equal to S. But we also know something else about F, and that is that because we're in limiting friction, it's about a slip, that F is equal to F max, and F max is equal to mu R, mu times this normal reaction force. So I can also say that mu R is equal to S, like that. Now, that we've done two things there, and if you remember from the previous video, what we said is that we are generally going to be writing down three equations, and one option is to have is to resolve in two different directions, and then to take moments about a particular point. So I'm going to take a anti-clockwise moments, and I need to decide on which point to take it about. Now, usually, what's going to work best is if you take the point that has the most forces acting on it. So in this case it's this point here, because this has got two different forces. If I take that as my pivot, then I don't need to worry about either of these ones, because they have zero distance from that point. Okay, so that's going to be the simplest one to choose. I'll give a name to that point. Let's call that point X. And so I'm taking anti-clockwise moments about X. So let's have a look at the moments of the various forces about point X. Let's start with one which is going to give me an anti-clockwise contribution, and that's this S. Now, think about the perpendicular distance from S to where the pivot is. So if I imagine extending that and thinking about this distance here, that's the same as the height of the ladder above the ground, which we worked out earlier was 4 root 3. So I can say S times 4 root 3 that's the contribution to the moment from that force there. And the other force which is acting is this mg, that's acting in a clockwise manner, so I've got mg and its perpendicular distance, it must be half of that distance there, so that must be 2. It's a distance of 2 from the pivot, so that needs to be multiplied by 2, and that equals 0. So now it's simply a case of combining information from these three different pictures together. Let's think about S. We know that S is equal to mu R, so here I could say mu R times 4 root 3. And I also know that R is equal to mg, so where I have that mg, that weight there, I can write that as R as well. And now R is in both of these terms, I could divide through by R, and I can say that that mu times 4 root 3 minus 2 equals 0. So having cancelled those R's, I can rearrange that, and I find that mu is 2 over 4 root 3, which I could simplify to an exact surd, or I can give that an approximate decimal value, which is 0.289. So in this next example, at first sight it seems similar to the previous one. We still have a uniform ladder, still got the length of 8 meters, and it's still 4 meters from the wall, so all of that geometry that we talked about earlier is still going to apply. So we can stick that information on there to start with. And this time we're told the weight of the ladder, which is interesting. That must presumably mean that we're going to need to use that weight. That weight is going to affect what happens in the question. It's still a smooth vertical wall, so there's still only going to be a normal reaction force there. There won't be any frictional force. We're told what the coefficient of friction is now. So we're told that mu equals 0.4. But it is still rough horizontal ground, so there'll be a normal reaction force R and a frictional force F. And what's different in this question is that this time we've got something else happening. We've got another object. We've got a man with a weight of 700 newtons, and he's climbing the ladder. And this is quite an important question in terms of real life applications, because if you're going to climb a ladder, you want to know if it's going to be safe to climb to the top, or if it's not, you want to know how far you can safely climb. So we want to know how far he can climb without it slipping. Now we don't know yet. It could turn out that he can get all the way to the top, but we don't know that yet. In fact, so what we've got to do, the way we've got to think about this is imagine that he's climbed so far that it is just on the point of slipping. So we'll call the distance that he's climbed x. So from this point here on the ground to some point along the ladder, it's difficult to fit this in, but imagine that we are measuring that distance that's been climbed along the ladder there. So between that point and that point, that's the thing that we're trying to find out, so we'll call that x. And just to avoid confusion then, we'll call this point here, I'll call that point P later for when we take moments. And at this point where the man is, we've got a force of 700 newtons acting downwards. Okay, so now we have all the forces in place. We're ready to take our resolve our forces and take our moments. And we might as well proceed in a similar way to how we did earlier. So starting with vertical forces and resolving those. So acting upwards on the ladder we have R. And acting downwards now we have the 250, which is the mass of the weight of the ladder. And we also have 700, which is the weight of the man. And that has to equal 0 to be in equilibrium. And that simply means that R is 950 newtons. Now if we resolve horizontally, we have F acting to the right and S acting to the left. So that has to equal 0. And so we can say that F is equal to S. But of course, because we're thinking about this, we're defining X to be the distance at which the man is just on the point of making the ladder slip. Again, we know that F is equal to F max. Okay, so I can replace that F with mu R. But this time we know what both mu and R are. We know that mu is 0.4. And we know that R is 950. Okay, so we know what the value of S is. Now one thing left to do is to take moments about P. So again, anti-clockwise moments about P. Acting in anti-clockwise manner, we have S times its perpendicular distance. So that's just the same as what we had before. So S times 4 root 3. And acting clockwise, we have 250 times 2. But we also have 700, and that needs to be multiplied by this distance here. I'm going to show that distance there. And if we think about the geometry of this, remembering that, for example, this angle here is 60 degrees, the hypotenuse of this triangle is x, this right angle triangle here, and we're talking about the side which is adjacent to the 60 degrees. Okay, so that will be x cos 60 degrees. And cos of 60 degrees, of course, is a half. So that's really just a half x. Okay. So the moment of that force will be 700 times that distance, which we've established as a half x. And that overall moment, again, will be 0. So, remember, we're trying to work out x, but we know already we've got this value of s. So I can put that value in here, and everything else is just a number. Okay, so the only thing here that's not a number is x. So it's straightforward then to rearrange that for x, and we find that x is 6.09 meters. So that concludes video 1.4, ladders. The final video on this topic will be 1.5, sliding and toppling.